Good morning, students. We are continuing with chapter 8. The topic which I am going to discuss in this video is EMF of a cell. Its full form is electromotive force of a cell. It is a term connected with the cells. And you have learned something about a cell. A cell has two electrodes and one electrolyte. Every cell has these features. Two electrodes immersed in an electrolyte. This is the structure of every cell. And this electrolyte is a chemical, and this chemical has positive and negative ions present in it. So these are the parts of a cell. Now let us see what is meant by EMF of a cell. This electrolyte has positively and negatively charged ions, and these negatively charged ions move towards an electrode. That depends on the nature of the electrode and nature of the ion. Anyhow, negatively charged ions, they move towards one of the electrodes and they impart electrons or donate electrons. On other hand, positively charged ions move towards the other electrode and there they are gaining electrons. In total, what happens is, due to the movement of this or due to the working of negatively and positively charged ions, one electrode will gain electrons, one electrode will lose electrons. The electrode which gains electron gets negative charge. For example, suppose this is the electrode gaining electrons, it gets negative charge, and the electrode which loses electrons gets positive charge. In one of the previous beginning videos I told, when a body gains electrons, it gets negative charge. When a body loses electrons, it gets positive charge. So here the two electrodes are getting oppositely charged. Means a potential difference will be created between the two electrodes. That potential difference between the two electrodes of a cell is known as EMF of a cell. And it is, since it is potential difference, it is measured in the unit called volt. Potential difference, its unit is volt. So EMF is also measured in volt. Then different cells are having different EMF. There are two factors that determine EMF of a cell. One is the nature of the electrolyte used and the material of the electrodes. These two factors, material of the electrodes and nature of the electrolyte used, that determines EMF of a cell. The next term is terminal potential difference or terminal voltage of a cell. Its symbol is capital letter V. Terminal voltage or terminal potential difference. Here I told every cell has some EMF. Potential difference between the two electrodes when the cell is not in use. Suppose you are using this cell. How to use a cell? How will you connect a bulb to a cell? You have to connect the two ends of the filament to the two electrodes of the cell. Look at the diagram. This resistor R symbolizes the filament of the bulb. And that filament or the bulb you have to connect across the two terminals, then it will work. Suppose this cell is of EMF 2 volt. Means when the cell was not in use, potential difference between the two terminals is 2 volt. Now the cell is in use, cell will work, electrons will flow from negatively charged electrode in this direction. Electrons will flow through this filament of the bulb and it returns here to the other electrode. When means the cell is in use now, that time if you measure how much potential difference is there across the two ends of this resistor, that potential difference is known as terminal voltage or terminal potential difference. In this example, I told this cell is of 2 volt. That means the cell can provide a potential difference of 2 volt. And when you use the cell, as I have shown here in the figure, if you measure how much potential difference this resistor gets, it will be less than 2 volt only. How will you measure the potential difference available across this resistor? For that you have to connect one voltmeter here. Across this resistor, connect a voltmeter. Voltmeter is always connected in parallel way. So this voltmeter will tell how much potential difference is available across R. For example, it may be 1.8 volt. That potential difference we call as terminal voltage or terminal potential difference. If the cell is of 2 volt, we expect a potential difference of 2 volt across the resistor, but it is not available. It is only 1.8 volt. Its reason we will see in the coming topic. Why a cell of 2 volt EMF can't provide a terminal voltage of 2 volt? Why there is some drop? The difference between these two, E minus V, we call as drop in potential. Here there is a drop in potential of 0.2 volt. The cell which is of 2 volt EMF is supposed to give 2 volt potential difference across the resistor, but it is providing little less only. For example, 1.8 volt. How much potential difference the cell can give when it is in use, that is known as terminal voltage. When the cell is not in use, how much is the potential difference across the terminals, that is known as EMF. When the cell is in use, how much is the potential difference across the terminals, or how much potential difference it can provide across the resistance, that is known as terminal voltage of a cell. And terminal voltage will be less than EMF. In our example, there is a difference of 0.2 volt. That difference we call as drop in potential. And its symbol is small letter v. Capital letter V is used for terminal voltage, small letter v is for drop in potential. So drop in potential is actually E minus V. So here the drop in potential is 2 minus 1.8, that is 0.2 volt. Drop in potential happened. Now we will see the reason for this drop in potential. Why there is drop in potential happens to a cell. So before that you must have some idea about working of an electric circuit. Here I have shown a simple electric circuit. This is the cell, 2 electrodes. This is of negative potential and this electrode is of positive potential, and this is the electrolyte. And here a device, any device or resistance, we call it as external resistance. And its symbol is capital letter R, is connected across the 2 terminals of a cell. And when you connect in such a way, electrons will move in this direction. Through this wire, electrons will move in this direction. It will move through the resistance R, then it will return to the other terminal of the cell. In this way, you will get an electron flow through this resistance. And these electrons flowing through this wire, electrons start from here, they reach here, and when the electrons move through this resistance R, electrons have to spend most of their energy due to the resistance of this material. These connection wires are made with the copper. Copper has very low resistance, so electrons can move very smoothly through this copper wire. But once they pass through this external resistance, due to its high resistance, electrons spend most of their energy and they come out as weak electrons. These weak electrons, they reach at the positive electrode. So remember the point, electrons moving through this section of the circuit are energetic electrons. After passing through the resistance, they come out as weak electrons. Means they spend most of their energy in this resistance. Suppose this resistance I have shown here is the filament of a bulb. Then that energy spent makes the filament hot and gives out heat and light. So what happens to these electrons which are weak? They reach here and they have to complete the circuit. Then what happens is the electrons which reached here reaches back to the negative terminal through the electrolyte. Like means electrons reach from here to here through the electrolyte. It is not like how the electrons move through the wire. Electrons reach from here to here by the chemical reaction. Okay, and while these electrons move between the two electrodes, this electrolyte provides some resistance. If you look at the complete path of the electrons, it is like this. It starts from here, it flows through the resistance R, reaches at the positive terminal, then from there it reaches back here through the electrolyte. So that electrolyte provides some resistance. That resistance we call as internal resistance. Its symbol is small letter R. This resistance we call as external resistance, and resistance of this electrolyte we call as internal resistance. So actually in this circuit there are two resistances involved. One invisible resistance is also there, that is the resistance of the electrolyte, which we call as internal resistance. Now let us go back to the drop in potential. This cell is of EM of 2 volt, but it provides a potential difference of a terminal voltage of 1.8 volt only to the external resistance. The reason is that remaining 0.2 volt, the difference of E and V, what we call as drop in potential, that is 0.2 volt, that is given to this internal resistance. So 2 volt the potential difference or EMF the cell is having, out of that 1.8 volt potential difference is given to the external resistance, 0.2 volt is given across this internal resistance. So 1.8 plus 0.2, 2 volt potential difference the cell is providing. So once again I will tell you the definition of EMF. EMF is the potential difference between the two terminals of a cell when it is not in use. Potential difference between the two terminals of the cell when it is in use is known as terminal voltage, capital letter V. EMF symbol is capital letter E. The difference of EMF and terminal voltage is known as drop in potential. Formula is E minus V. In our example, it is 0.2 volt. And why this drop in potential happens? It is due to internal resistance of the cell. Now, already I gave the definition of EMF, terminal voltage and drop in potential. These three terms can be defined in one more method. Listen to it. Imagine one coulomb charge moves from one electrode to the other electrode through this external resistance R. I mean 1 coulomb charge means it is 6.25 into 10 to the power 18 electrons. Start from this negatively charged electron. It moves through this external resistance R, capital letter R, and reaches back at the other electrode. Then what happens is from that electrode, the same charge reaches to the starting point again. Then the complete circuit is completed. During this path or journey, how much work is done by 1 coulomb charge? That is also defined as EMF of a cell. EMF of a cell is the work done by unit charge, means 1 coulomb charge. Why it moves the entire circuit? Entire circuit means from one electrode, it reaches to the other electrode through the external circuit or external resistance, and from there it reaches back to the starting point. Then we call the circuit is completed. During this journey, how much work is done by 1 coulomb charge? That is EMF. Next definition, for terminal voltage also you can define in terms of work done. Terminal voltage is the work done by unit charge while it moves from one electrode to other electrode through this external resistance. Means 1 coulomb of charge moves from one electrode to other electrode, means reaches from here to here. During that time it covers or passes through capital letter R only. That time what is the work done? That is known as terminal voltage. Now what is the meaning of drop in potential? If 1 coulomb of charge moves from one electrode to other electrode through the electrolyte, internally it moves. Then what is the work done by unit charge? It is known as drop in potential. In this way, or in terms of work done also, you can define these three terms. Now something more about internal resistance of a cell. The definition is, it is the resistance provided by the electrolyte of a cell. This internal resistance depends on certain factors. First factor is, it depends on the surface area of the electrodes. More the surface area of electrodes, less will be the internal resistance. That is the first factor. Second factor, temperature of this electrolyte. If it is high, less will be the internal resistance. Then third factor, distance between the two electrodes. If it is less will be the internal resistance. And another one is density or concentration of this electrolyte. If it is high will be the internal resistance. So there are 4 factors that determine internal resistance of a cell. These 4 points already I told. Now this internal resistance of a cell, if it is 0, I mean if the cell has no internal resistance, this resistance we assume as 0. For such cells, E and V are equal. This EMF and terminal voltage will be equal if the internal resistance is 0. If the internal resistance is not 0, means if the cell has some internal resistance, in that case E will be greater than V. Okay, and remember one more point, while a cell or battery charges, charging time, reverse will be the case. E will be less than V. That topic doesn't come in your syllabus. Now let us see how to calculate this EMF, terminal voltage and drop in potential. Suppose I is the current flowing in the circuit. Current flowing in this circuit is I. Then EMF, you know, it is the potential difference. According to Ohm's law, potential difference is the product of current and resistance. V is equal to I into R. Potential difference is I into R, current into resistance. So here EMF is actually potential difference. So we can use that formula. So formula for EMF is current into total resistance, that is R plus R. We have to consider both the resistances. External resistance capital letter R and internal resistance small letter r. Then what is the formula for terminal voltage? Capital letter V. That is the product of current into external resistance. I into R, it will give the terminal voltage. I into total resistance will give EMF. Then how will you get drop in potential, small letter V? That is I into small letter R. Current into current flowing through this small letter R or internal resistance is I only. So I into small letter R will give drop in potential. And you have to learn these three equations. All these three are potential differences, so they can be written as the product of current into resistance. In case of EMF, total resistance R plus R is to be considered. In case of terminal voltage, only external resistance is to be considered. In case of drop in potential, only internal resistance is to be considered. Now let us discuss some numericals based on these equations. In your textbook, they have made some equations by combining this. It is not necessary. You may just directly apply these equations. That is enough. Listen to some of the sampled numericals. From page number 175, question example number 1. 175 page number, question number 1. This is the question. The reading of a voltmeter when connected with the 2.2 volt cell and resistance of 5 ohm is also connected with the terminals of the cell. Voltmeter shows 1.8 volt. Calculate the internal resistance of the cell. A cell is connected, cell of EMF 2.2 volt. Let me draw the figure. This is the symbol of a cell. Long line represents positive terminal and short line represents negative terminal. It is connected across a resistance. And this cell is of EMF 2.2 volt and it is connected across a resistor of 5 ohm. And the voltmeter which is connected across, if you want to measure how much terminal voltage this resistance gets, you have to connect one voltmeter. Always connect the voltmeter parallelly across the resistor. I mean, if you want to know how much is the potential difference across this 5 ohm resistor, you have to connect one voltmeter here. Okay, current will flow in this way from positive to negative. The current flow will happen in this way. There will not be any current flow happening through this voltmeter. Current flow completes. It will flow through the resistance and returns here. In this way there will be flow of current while the circuit works. So when you connect this voltmeter, the reading shown by the voltmeter is 1.8 volt. That means capital letter V is 1.8 volt. Terminal voltage is 1.8 volt. EMF is 2.2 volt. Calculate the internal resistance of the cell. This cell has some internal resistance that you have to calculate. How to proceed with? You have E value, R value and V value. Small letter R you have to find out. First, by using this formula, V is equal to I into R, you can find out how much is the current flowing. Use the formula V is equal to I into R. V is here, R is here. So I you can calculate. I is equal to V by R. V, capital letter V, 1.8 upon R is 5. 0.36 ampere current will be flowing through the circuit. V 1.8 by R 5. Okay, so the current is 0.36 ampere. Now how to find out small letter r? You can use this formula. E is equal to I into R plus R. E is available 2.2. I you got here, and R, capital letter R is 5 ohm, small letter r is unknown. You can apply the formula and get the value of small letter r. Next question. Question number 2, same page. A cell of EMF 2 volt and internal resistance 0.2 ohm is connected to a 3.8 ohm external resistance. Calculate the terminal voltage. Almost the same application. Let me draw the diagram. See how to solve example 2. This is the circuit diagram. There is a cell of 2 volt EMF having internal resistance 0.2 ohm. It is connected across an external resistance of 3.8 volt. What is the terminal voltage? V. V, its formula is I into R. Current into external resistance. R is here but I is not given. I you have to find out first, then you can find out V. For finding out I, you can use the first formula. E is equal to I into R plus R. E is 2 volt. Capital letter R is given here, small letter r is given here. So you can find out I, then I you multiply with R, then you will get the terminal voltage V. I skip the calculation. I think you can understand the method. Next example, page number 175, example 3. A cell gives a current of 0.5 ampere with an external resistance of 12 ohm and a current of 0.25 ampere with an external resistance of 25 ohm. Calculate the internal resistance and EMF of a cell. A cell is connected across a resistor of 12 ohm. This resistance is of 12 ohm. And the cell is connected here. Its EMF is not given, internal resistance also is not given. You have to calculate both. It is given that the current flowing here I is 0.5 ampere. A cell connected across a resistor of 12 ohm makes a current of 0.5 ampere. Then same cell is connected across another resistance of 25 ohm. The same cell is used here, so E and E up. You can use the same symbol, same cell. But the resistance is changed. Here it was 12 ohm, but here it is 25 ohm. This time current is 0.25 ampere. I value is 0.25 ampere. Then how will you find out EMF and terminal voltage of the cell? You can use the first formula. E is equal to I into R plus R. Apply the formula in both cases. In first case you will get it as E is equal to, E is unknown, I is given 0.5 into R plus R. R, capital letter R is 12 plus small letter r unknown. This is equation number 1. Apply the same equation in this case. First equation, then you will get E is equal to I into, that is 0.25, R plus R means 25 plus small letter r. Equation number 2. Here you have two equations with the two variables. So you can solve the two equations and get the value of E and R. Next example from page number 179, question number 2. Numerical number 2. The EMF of a cell is 2 volt. Look at the diagram. And On connecting it with a resistance of 18 ohm, the terminal voltage of the cell drops to 1.8 volt. Means capital letter V is 1.8 volt. Cell is of 2 volt, but when it is connected across a resistor, it gives a terminal voltage of 1.8 volt. Calculate the internal resistance of the cell. This R you have to find out. How will you follow? From V and R, you can find out I by applying this formula. V is equal to I into R. I you can calculate. I is equal to V by R. V is 1.8, R is 18. That is 0.1. Current you got as 0.1 ampere. Now use the first formula, or you may use this formula also, no problem. You may use either first or third formula. E is equal to I into R plus R. E is 2 volt. I you got as 0.1 ampere. Capital letter R is here, small letter r is unknown. You can solve and get it. Now next question 3. A wire of resistance 20 ohm is kept in circular form. Calculate the equivalent resistance between the ends of the diameter of the circle. With a wire of 20 ohm resistance, a circle is made. And if you make a diameter, between the two ends of the diameter, what will be the resistance? Means between these 2 points, this is the diameter. Between these 2 points means only half length of the wire is included. So the resistance will be half of 20, that is 10 ohm. Listen some more numericals related to the same topic from page number 183, first numerical. 183, first numerical. A cell supplies a current of 0.6 ampere through 2 ohm resistance coil and a current of 0.3 ampere through another 8 ohm coil. A similar type of question is solved. Calculate the EMF and internal resistance of the cell. Same cell, it is connected with the 2 different resistors of different resistance and current is different. Then you have to find out E and R. Already have shown the sample for it. Next, page number 187. Question number 32. A music system draws current of 400 million ampere when connected to a 12 volt battery. This is the music system. It is connected across a battery of 12 volt. A music system is connected across a 12 volt battery. What is the resistance of the music system? In this case, about the internal resistance of the cell, nothing is mentioned. Means small letter r is, if it is not given, you assume it as 0. If small letter r is 0, look at the equation, this r becomes 0 means E and V becomes same. I into R here also I into R. In that case, E and V are equal. Already I mentioned that point earlier. So here in this case, since internal resistance is negligible, this E and capital letter V, EMF and terminal voltage, we can assume as 2 volt. Because R is 0. If R is 0, these two are same. E and V are same. Then what is the first question? What is the resistance of the music system? What is its R value? And the current flowing here is given. I is equal to 400 milliampere. Milli means 10 to the power minus 3 or you have to convert this from milliampere to ampere. For that you have to multiply with the 10 to the power minus 3. Milli means 10 to the power minus 3. That means 0.4 ampere. This number is 0.4 ampere. So current here is 0.4 ampere. How will you find out R? Use this formula. V is equal to I into R. V is 12 volt. I is 0.4. Then you will get resistance of the music system. We solve. V is equal to I into R. V is 12. I 0.4 into R. So R is equal to 12 by 0.4. 120 minus 4. That means 30 ohm. Resistance of this music system is 30 ohm. What the calculation as 30 ohm. Now second part, this music system left playing for several hours, and finally the battery voltage drops and the music system stops playing when the current drops to 320 milliampere. This music system it works for some hours and it stops functioning when current becomes 320 milliampere. Current I value, it becomes 320 milliampere means 0.32 ampere. When I value becomes 0.32 ampere, the music system stops playing. And this resistance, you know, it's a fixed value. Whether the instrument works or not, resistance of this device is 30 ohm. It is not changing. And you are asked to find out if the system stops at this current. Earlier it was 0.4 ampere. Now the current, when it becomes 0.32 ampere, the music system stops. So at what battery voltage does the music system stop playing? At this point, what must be the voltage? Voltage might have dropped. At what voltage the music system stopped functioning? So to find out that, again use the formula. V is equal to I into R. R is 30. Now the I is 0.32. So this I you multiply with R. That will be the V, or terminal voltage of the cell. At that voltage the system stops functioning.